last time. So about this HDB, high duality violations, or generalized symmetries in this particular way of describing them. So I will draw some region, topologically non-trivial region. Here will be some region that is a kind of ring in 4 dimensions or higher dimensions. Then we have this operator here, A, and this B operator in the complementary region that are the non-local operators. And it can be the Wilson loop and the Toff loop, for example, in 4 dimensions. In 4 dimensions also you have Wilson loop and Toff loop in both regions. So I was calling the maximal algebra of some region R equal to the commutant of the algebra that is outside. A is an algebra that is additive, and the commutant, so is, for example, all operators here. I take the commutant, the Wilson loop commutes with everything outside, and then belongs to the maximal algebra. And it's non-local because it cannot be produced locally. It's not additive inside. So this was the complementarity diagram. The algebra, the additive algebra is included in the maximal algebra, and this is equal to the additive algebra plus some non-local operators, and complementarily, in the complementary region, taking commutants, we have the maximal algebra of the complementary region that includes the additive algebra of the complementary region, and is equal to the additive algebra of the complementary region plus some non-local operators B, right? So some comments. When there are no high duality violation, we say that the theory is complete in the usual sense that you have charges, maximal net of charges, let's say, that convert these non-local operators into local ones. The non-local operators come always in dual pairs, the A's and B's, which do not commute to each other, all of them at least. And the size of the non-local operators of the dual regions is the same. I will say more about what is the size tomorrow. They are topological. Topological or transportable. So you can deform the region and you get the same kind of sectors, the same kind of non-local classes. And this idea is behind the idea that if you have these non-local classes, this situation for some region, then you have it for any deformation, and then it means that as you change the scale, for example, you will have the same structure, and then it means that goes along the normalization group flow the same. It is kept the generalized symmetry or these has duality violations along the normalization group flow. This transportability we think is always the case for relativistic theories. We have seen that this is not the case, for example, for fractons, where in Fiona's lecture, where these things cannot be transported or deformed in any shape. So one important thing is that when you have this type of problem or features, the high duality violations, you can put more than one algebra that is compatible with causality with the additive operator. So you have the additive algebra, and you have the additive algebra. The maximal algebra is also compatible with causality with the additive operators outside. So I wanted to say a few. As I mentioned, we started working on this directly, thinking these things in entropies, etc. And then we kind of rediscovered what people was talking about generalized symmetries that was proposed a few years ago. And then everything more or less matches what everybody says, especially on John's lectures today, that he was not using other topologies for the manifolds for doing things. So it's very, very similar to this description. You have the topological operators. But still, we find some differences, perhaps not much important, but still there are some differences. And I wanted to mention them. So the first difference is that the dual operators here, the A's and B's, are completely in equal footing. In the description, they are completely in the same footing. And people in the generalized symmetry literature tends to classify, for example, some of them say that they are genuine line operators, and the other are topological surface operators, and we don't see any distinction that can be made physical on this setup. For us, both of them are line operators in the sense of causality, because both of them live in a region and commutes with local operators outside. For example, the B commutes with the local operators outside, and the same for the A's. And both of them can be thought as surface operators in the sense that in the sense of additivity. If you want to produce the A and the B in terms of local operators, you will need a surface to write them. For example, a Wilson loop is a flux of magnetic flux, and the same for the Toff loop. So this is a difference. So as far as people do not put much attention into this difference of line operators and surface topological operators, then we agree everything. But this will be especially important for Javier's lecture, Javier's seminar next week. He talk about the ABJ anomaly. So, and related to this, the second kind of difference is that people talk about theories. So I was mentioning before that you have the additive algebra for a region, and this is included in the maximal algebra, right? This is a net, it's an additive net, causal net. Net means that we can have an algebra for any region inside, whatever. Additive because it's additive, and causal is because it commutes at special distances. This is not a causal net. Because non-local operators for spatially separated complementary region do not commute, right? So this is not a causal net, but you could play the game of enlarging your additive net and still producing a causal net, just adding non-local operators. Some of them, not all of them. So, and then you arrive to some maximal causal net that we can call a Haack-Dirac net, right? And it seems that in the literature of generalized symmetries, people turn to pay much attention into the Haack-Dirac nets, and they even label theories as different if they have different Haack-Dirac nets. Yes? Net is just an algebra for any region. So that satisfies some property. For example, for a region that is smaller, it's included, the algebra is included. But then this other net can be additive or cannot be additive. It's just if you touch two regions and produce the generated algebra, it will give you the, for example, if you have these two balls, it depends on whether the algebra of this plus the algebra of this, the generated algebra is equal to the generated algebra of this. So if you start with field operators, you always get an additive algebra, right? But if I add to my ring and a non-local operator, then it's not additive anymore. So this Haack-Dirac net has the property that is a Haack dual, but not additive. So it's not a normal additive net that is Haack dual. You have not complete. It's not complete. Because completion is Haack duality for the additive algebra. So you have both properties together. So somehow what's happening is that you can have an additive algebra that is not Haack dual, or a Haack dual net, but it's not additive. So you have to give up on one of those properties. So I was saying that people sometimes label theory with this. For example, I was mentioning that the free Maxwell field people call the compactified field just taking a close algebra of non-local operators, such that is a Haack-Dirac net, right? And if you think physically, they are indistinguishable. These theories are indistinguishable. This is just a choice, right? Why? Because the non-local operators are already local operators in balls. So the operators you have accessible are the same. So this is a description of some features, some textures on the algebras. But the theory, it doesn't matter what you do, what you choose as an algebra for a region or not, right? It's the same thing. The operators are the same. Exactly. For me, it's exactly the same. I was going to say that in a few minutes, but I will go through this again in a few minutes. Yes. Well, that was my perplexity today, because you said that the topological theory you can obtain as spontaneous symmetry breaking of a generalized symmetry, and then in the case, for example, AC2, you have a confinement, and you say, well, this is not spontaneous symmetry breaking, but then you would say that it's topological the case of the usual case of spontaneous symmetry breaking, you will say that is topological, and not in the case of confinement. Oh, but these are the same. So you mean, well, better we go again through this thing when I mention these non-abelian things. Okay. But then, well, this approach to general symmetries is about these commutators, etc., that perhaps from the point of view of high energy looks like complicated, more complicated than the usual description, but for a lattice guy, it is something that you have access, immediate access. You have the local algebra, is finite dimensional algebra, and then this is a kind of invitation also to condensed matter people also to think in this way. The only feature that is somehow better in the continuum is that you don't have centers, you don't have nothing in the boundary, while if you have a lattice, you have to choose your algebras in the boundary, and then you could have, you have to be careful in doing that in order not to produce high-duality evaluations that are kind of ultraviolet stuff that you are putting there, right? You want to describe the long-distance objects only. But one thing one can say, for example, is that if your lattice, already died. If you can divide your lattice in a square, let's say, in squares, I'm not, and the Hilbert space or the algebra is a tensor product of each square, then you don't have any generalized symmetries or any High duality violations. This is because if you draw some region here, the commutant will be directly this additive, the missing squares. So you already know that this cannot have any High duality violations. So it means that you can say the same in the continuum. In the continuum, you can say the same if you think these squares are type 1. Type 1 is usual algebra of operators in a Hilbert space, not a type 3 that this. So if you think there is a property, it's called the split property, that allows you to divide the algebra of operators, for example, inside and outside, and in the middle is non-local. A little bit non-local can be very small, this thing, and then you have a ordinary tensor product of what is going on inside with what is going on outside. This is not possible if this line that I'm drawing here is a sharp line in space, because that type of algebras are type 3 algebras, and then they do not have this tensor product structure. But you can little regularize the thing in order to have a tensor product structure like you would expect in a lattice, for example. And then if you can do these multiple splits in such a way that this is a ordinary tensor product, then you don't have any generalized symmetries, any High duality violations, and then it must be the case that when you have High duality violations, you cannot do these splittings, right? You can split always into two, but not in many different regions locally. Well, that you can say better than me, but of course, if you work in a lattice with the tensor product structure, yeah, I would say, well, you can have, for example, a global symmetry, but if you think that you are interested in the neutral part of the algebra, then it's not going to be a tensor product. That's it. But in the case of the Wilson loops, that is not available for you. So already in the case of the Wilson loop, you need that you cannot describe this as a tensor with a tensor product square, because exactly. Something like a gauge theory you need, right? So let me then begin where I left last time in QED. I wanted to say a few things more about QED. In QED, you also have this current, J mu, that is conserved. And then you can say, well, what happens if I take this current and I have a global symmetry with this? Well, this is not the same type of stuff as the usual global symmetry, and the reason is that J mu is equal to d nu f mu nu. So when you take your G0 to construct a charge in some region and integrate, this will be the flux of the electric flux on the boundary, right? So this that was supposed to be the non-local operator for the global symmetry is a boundary operator. It's a local in the boundary, so it's additive in the boundary. It's not non-local. So you cannot, so in this sense, the usual electromagnetic charge does not give you ordinary global symmetry. And the same happens for the complementary things. In the global symmetry, you have these non-local operators, the plus and minus, the different charges, but then now they have to be linked by a Wilson line that will not commute with the outside. So really, this object is not something belonging to the two balls, but it has to belong to some region like this. It's an additive operator inside. So in a sense, when you have a conserved charge, a conserved current, or a conserved form field, a conserved current, for example, this is going to give you a high duality violation for the neutral part only if it is not exact. So the same happens with F mu nu. So you have, let me pull it. You have df equal to 0, so it's a closed form, but it is not. You would say from that I get that f is equal to dA, right? But this is not gauge invariant, so somehow the high duality violation will appear when you have closed forms, fields, that are not exact. Somehow it's kind of a quantum cohomology, because for normal classical fields, you would say, well, this solves the thing, right? It's always that I have this, but here we are not allowing this object because it's not a well-defined quantum operator. So it's kind of quantum cohomology, and it's also generalized to cases where you don't have a continuous symmetry, but a discrete symmetry, where you cannot write the generators of the symmetry as the fluxes of something, right? And another thing that I wanted to say about this is that this allows us to think on a different kind of high duality violations that are related to topological theories. Because in all this description, I need local operators to say something, right? So typically, people, if you think in the topological theory itself, doesn't have a local degrees of freedom, so where are these generalized symmetries for topological theories? Well, in general, you know many kind of topological theories. I do not know if all of them can be described with this type of stuff, but for some of them, if you have a gauge charge, you can say these charges cannot be alone. It has to have a flux going to infinity, for example. And then this type of thing will produce, once you keep only in the sector where the vacuum sector where all charges, the global charge is 0, that it will produce high duality violations for regions that are cones that goes to infinity. Are cones that go to infinity. So you can think of this as something that is related to topologies related to the boundary. Here is two disconnected regions, for example, in the boundary. Yeah, you could. And that would also have yeah, but this is a different operator, right? It's a different operator.
So,
No. I'm saying that I'm saying just that the operator content of the model has these operators, right? And then if I keep myself in the, it's like the case of, I say that this case is a non-local operator. You have a plus charge and minus charge. It's a non-local operator because I'm keeping in the neutral part of the algebra, right? So this cannot be generated locally. So this cannot be generated locally inside here. This cannot be generated locally, but still this operator is in the whole algebra. Okay? So this kind of topological things was described by Buchholz and Fredenhagen in 1982. So it's quite old stuff in the literature of algebraic quantum field theory. So I want to say something also about non-abelian theories. Very little, because many people already know that. And in this case, again, we have in principle, in some ring like region, we have some Wilson loop, for example, that is the trace of the path integral and exponential. And here I have to choose some representation, and then the Wilson loop will be labeled by representations. But these operators are not always non-additive, not always non-local, and the reason is that the F mu nu is always there, and the F mu nu is a charge operator in the adjoint representation, so F mu nu x this thing will be a Wilson line that destroys the non-locality of the adjoint representation, the adjoint Wilson loop, and will also destroy the non-locality of all Wilson loops generated in the algebra of the adjoint representation. And then you can ask what are the only loops that are non-local, and it turns out that these are labeled by representations of the center of the group, of the gauge group. So you have to have a center, let me call it Z, of the gauge group. Otherwise, you don't have any non-local operator. And for example, for SUN, the center is just Zn. And then you will have representations of this center, and this representation of an abelian group also form a group that is called a dual group, just because it's a group of the characters. It's a group of the characters. The characters form a group, and this is the dual group. So, for example, typically for example, for SU2, you have the fundamental representation that is the non-local, is the only non-local. For SU2 is Z2. So it's the only non-local operator here. And complementarily, the top loops will be labeled by elements that belong to the center of the group. So they are labeled by elements of the group, or the center of the group. Well, and the commutation relations are always fixed. This is a face, because it's a one-dimensional representation, is the character of the element. These can all be completely completely proved and shown in the lattice, that these are the only non-local operators. And I wanted to say something about some point that maybe some people is doubtful about, and many people have told me about that they do not know how. If you go to the lattice and you describe the top loop, it's very easy to see that the top loop is additive in a surface, because it's just a product of things in the surface that also are. But what is not clear is that the Wilson loop is additive in a surface. Suppose you have the electromagnetic field, the Wilson loop will be a flux of magnetic flux, and then it's trivially additive in a surface, not in a line, right? But it's trivially additive in a surface. You would like to do the same for the non-abelian field, but it's difficult to understand how this is produced locally. And there are some non-abelian Stokes theorems, but these do not do the job, because they put the Wilson loop as something in the middle, but the something is usually non-gauge invariant. The expression is not gauge invariant. So I wanted to say something about that, because we have shown this in our paper, and because the trick is that you need electric fields also to express the Wilson loop as a flux. So, the idea that now you have a lattice, and your variables are these elements of the group that belongs to the gauge group, and they are on each line, and then you have here these gauge transformations, and this transformation is G. Or let me call it AB at the link, AB, GA, right, this is a gauge transformation, and then you can say, well, what is the Hilbert space here? The Hilbert space is all the functionals of the U variables in the lattice, but that is gauge invariant. Then you can describe how to write a Wilson loop. Here is easy. I will not go through this, but I will go through the description of the electric fields. The electric fields are, you can think some operator that acts on the wave function, that is a wave function of the elements of the lattice, and in the link L, these are labeled by links. In the link L, it multiplies, let me see what I put here. It multiplies by the element G. So it takes one element of the link and multiplies by G. And you can see that this is not gauge invariant operator. In order to make it gauge invariant, you have to sum of these elements. Let me call it electric field of some link is equal to a sum. And now depends on the conjugacy class of the group. You have to sum over the elements of the group belonging to some conjugacy class. And this is gauge invariant. And then you can also produce other operators out of this, electric operators. That are projectors this is the character of the group, and then it's invariant the conjugacy classes. So this thing is a sum of these electric operators, right? It's a combination, but it has the property that how projects on the representations. So you have that this PL R dagger is equal to PL is Hermitian, and are projections, and the sum of these is equal to the identity. And then how you construct Wilson loops that are big out of Wilson loops that are small. Let us take two Wilson loops that are, or can be any size, can be two plaquettes, but share a link. And I have to take it with the same representation. Then it follows that the sum of these two, the product of these two, in the abelian case, this will give you just already the full Wilson loop, but now you make the product, and the problem is that the representation of the Wilson loop, when you multiply, will give you several representations, not only one. So you have to project with these local electric fields in the link in order to get what you want. You get the full Wilson loop. So in that sense, a big Wilson loop is formed by plaquette operators multiplied with some, in the algebra of plaquette operators, and some electric projectors. So this shows in the lattice the fact that the Wilson loop is additive in a ball. So this is what I wanted to say about the non-abelian case, and I get again to the point that we were discussing before, that for example for SU2, let me call this discussion SU2 versus SO3. If you have a lattice, then these are two different groups, and then you put different groups on the links, and you have different models. For SO3 doesn't have a center, so it means that it doesn't have any non-local Hugh-Duality violations, while SU2 have a set 2 of non-local operators. So these are different in the lattice. Now, if you go to the continuum limit, then it can happen that you have, in the continuum limit, you expect to describe your theory by a Lagrangian that only depends on the Lie algebra. And then it can happen several things. That it can happen that this is going to give you the same thing, the same Lagrangian, plus some charges that will break the non-local operators. Or it could happen that this will give you SU2 without any other charges that remain in the lattice. I don't know the answer to that. I don't know if it is known, this thing, what happens when you go to a continuum limit of SO3 in the lattice, but it can be both, right? But this naming that is natural, because you name it the theory with a gauge group, is not the one that people in generalized symmetry uses. They have an SU2 theory in the continuum, and they label it as SU2 if it has the Wilson loop, for example, and as SO3 if it has the Toff loop, as I understand. But this is not possible, right? You have both operators at the same time, or you don't have nothing. That's the point. So you cannot have the Wilson loop and not the Toff loop, or you have to have both. This is obligatory because of the fact that the non-local operators come in dual pairs. Cannot be. So we really don't understand how to understand what they are thinking about in this case. Probably what we think is that they are labeling by Haq-Dirac nets in the sense that they are taking for the loop one of the operators, and then they are taking different names for different Haq-Dirac nets. And they are trying to make it more physical. If you put this thing in a non-trivial topological manifold, then there is a global one, a global Wilson loop that you can choose one or the other, right? And these are two theories. But locally, the same thing will be going on. So you will have both, right? So no objections. No objections? No comments. Okay. Yeah, but in what sense? So it's non-physical. No, there is no physical way to differentiate these two things. It's just the way you write it down, because one is an integral of A mu, but A mu is non-physical. So in this sense, it's more tied to the way you write your theory in your Lagrangian or what are your variables, right? But not something physical that I can detect with measurements. Well, but on the torus. Yeah, but then it depends on how you define your theory in the torus. That is not. So if you have the SU2 theory in flat space, and you will say, well, I will take it to the torus, but it depends on your choices there, right? So it can have, you can have some choices. So I think from our point of view, it's something that is not wrong, but is some naming, some way of thinking that is confusing things. Because the important point from our point of view is that is the point that you have more than one algebra for the same region, so you can choose different things. This is the key point in this thing. So taking one choice is already like confusing the fact that the phenomenon is about having many choices, right? This is our point. Well, I will not talk about more about this, and well, what I wanted to say now is some things that are known about, because you can say, well, these Haq duality violations will depend on the region. it will depend on a specific topology. So you can say, well, what are the possibilities I have for these non-local operators? What are the possibilities for the fusion rules, the commutation relations, etc., right? Well, and some things are known, at least for the cases of these rings and separated balls that I have described. In D greater or equal to 3, Hug duality violations for several balls, for disconnected regions. Come exactly as I have made in the examples, come from the neutral part of a global symmetry group. Symmetry group is a group. So, and the same happens. So these cases were the cases where p pi 0 and p pi d minus 2 of R are non-trivial. So in these cases, what happens? Well, and the group can be abelian and non-abelian. No, the group can be non-abelian. In these cases, what happens is that you started with some net of algebras that have duality violations for one ball, in the case of spontaneous symmetry, or for many balls, and then you can extend it. So you can extend it. So you started with some algebra. You can extend it to some another additive algebra. Just you can say that such that this F quotiented by the group G is O. This is people call it this observable algebra, and this is the field algebra. This is the name of the letters there. So so you can always extend the theory in order to kill this eliminates these Hug duality violations. So you can cure the Hug duality violations by extending the theory to a charge operators. You can say like that, but the idea is that you want to classify Hug duality violations. So some people give you some Hug duality violations for several regions, and you can say, well, I can always cure this, and in such a way the inverse operation of the usual, yes, engage in it somehow, yeah. And this extension is an extension in the sense that these are included in the algebra of F, and the Hamiltonian is the same, and the correlators in the O part of F is the same. So it's exactly subalgebra of the other, right? This extension is unique. So what happened in D equal to 2? Well, there you can have, in this case, is several intervals. Several intervals. In this case, what happens is that, as is well known, the fusion and the commutation relation is more complicated and is described by a category. And in general, it can be extended to eliminate Hug duality violations. but in a non-unique way. In general, it's not unique. The extension is non-unique. This will be the subject of the talk of Valentin Benedetti next week, and there is a relation between the complete theories when you have extended with modular invariance. So these theories that have these high-degree violations violate modular invariance, S modular invariant, and in general the extension is not unique. For example, the stress tensor for central charge equal to 1/2 can have a fermionic extension in the term of a fermion, or can have an Ising model extension in a bosonic extension. And there are other central charges that have many, well, some purely bosonic extensions, maximal extensions. So this is a difference with dimension greater than 2. For dimension d greater or equal to 4, and regions that have a pi, pi 1, etc., and pi d minus 3. In this case, you have all the non-local operators form dual abelian groups. And this will be discussed briefly by Javier next week, how you show that. What happens for topological, for sectors? Cone-like sectors, they say. As we draw before, you have these cones, right? Well, what happens is exactly the same as what happened with all this, but for one dimension less, because it depends on the type of thing you have in the boundary. Here you have disconnected regions, so you have to use these theorems, these ideas, on one dimension less. So, for example, in 3 dimensions, you can have this type of category theory symmetries. And in 4 dimensions, if these are corresponding to disconnected regions, the type of high duality violation you obtain are groups. So I wanted to remark in relation to this some commentary about this idea of non-invertible symmetries. Yeah.
So can you reinterpret what you just said about what you get in space-time dimension 4 and greater in terms of a statement about what kinds of generalized symmetries / topological? Because you said they're all group-like.
Yeah, I will comment exactly about this.
Okay. Yeah.
Yeah.
The question is, like, does this suggest that all topological orders in
Are groups. Yeah, that's it. So you. So I would like. So this thing that I said here is a Doppler-Hart-Roberts DHR theorem. That is from the 71. So it's some series of papers from the 71 to 89. Took many years in the making. And so what I wanted to discuss is somehow the meaning of this theorem in this sense. So it's important that the original setup of this Doppler-Hart-Roberts theorem is not exactly about High duality violations, but about superselection sectors. Superselection sector of the theory, but there is a way to connect these two things. This was already known, but in the way they describe the things, they do not pay much attention to High duality violations, but it was already known at the time. So in this language of High duality violations, there are some people that have already made some comparison with this. If you start the High duality violations, how you get this theorem in 2 dimensions is completely known, and if you see this translates to higher dimensions the same, and we are doing some paper with Javier about that. It's important to uplift the ideas of High duality of Doppler-Hart-Roberts here from the superselection sector stuff to High duality violations, because, for example, for sectors with rings, you don't have any superselection sector because of the ring. You only have High duality violations. So it's a more general to talk and think about High duality violations than superselection sectors. So what I wanted to say here is that suppose you have as people usually think, you have a topological operator, some operator, that is topological and means that it commutes with the T mu nu inside, right? So it means that it will not commute with other operators inside, for example. But then it means that it commutes with something. It means that there is a subalgebra with which it commutes. So subalgebra that commutes with the topological operator. And so immediately in this subalgebra, this topological operator will be some non-local thing in the boundary. So you will have exactly High duality violations for regions of 2 volts, etc. And then you could immerse that. If you complete canonically the theory of the T mu nu or whatever it is there, then this operator should be one of these twists that appear in this setup. So once you have completed the theory, your topological operator will be one of these things. So it doesn't mean exactly that this topological operator will be invertible from the beginning, but if you take the algebra of non-local operators, it will be part of that algebra. This is the idea. So it could be non-invertible, but in a kind of trivial way. For example, if you have some theory T1, including some theory T2, and then you complete this, this is related to this with a group. This is related to this is complete. This is related to this with some other group, H. But the relation between these two is maybe it's not a group if this is not a normal subgroup, right? It can be coset or something like that. So if you are thinking in this, maybe you can cook up some operators that look like non-local, and that they do not have a fusion of a group. But still, if you complete, you can see that all is going to be group-like. Okay, how much time I have? Okay, so I will change subject now to some application. And this application is about the Nether theorem. And some abstractions to Nether theorem. So then the idea now is that you have a global group, global symmetry group, global in the sense, the usual sense, not a generalized symmetry, global group, a global symmetry group, and a continuous one. And you want to understand whether there is another current related to that or not. In general, there will be, but there are some exceptions that are known, well known, and we want to understand this in the setup of this high-duality violation, how this plays a role there. So, and then we will be looking at theories with a global symmetry group, but which also have high-duality violations. Then it can happen two things. One is that the group does not mix the non-local classes, and the other thing is that the non-local classes are charged. And then, in general, what you have is that, suppose you have some region that I will draw like, this can have any topology, but I will draw it as a ball because of simplicity. And then I want to have a twist of the global group, some that applies the symmetry only in region R. And then I will need some little smoothing region here to produce my twist. So the twist will act inside R as the usual group, but only for the additive algebra in principle. So, but then in this situation, you can have a refinement of the type of twist you can have. You can have your twist can be additive. It can be additive if it is an additive element. Is it additive in R union Z, let's say? Z is the smoothing region. And tau can be complete if acts as the global group on the maximal algebra of R. So your twist is complete if it moves the non-local operators that R can have in the way that the global group does. And it's additive if you can construct it additively in this region, right? It can be seen that both type of twists can be always constructed. So you can always construct this type of twist and this type of twist. No problem with that. Sorry? No, in general, they are not, but when you have a twist that is additive plus complete, then it means that the symmetry does not, or your generalized symmetry or the non-local classes, let's say, is not charged. If you can find a twist that is both things together, immediately the non-local operators cannot be moved by the symmetry. I mean, the classes cannot be moved. And the reason is that as the twist is additive, it cannot change the non-local classes because additive operators cannot change non-local classes by definition. And as it is complete, it means that the global group do the same. It means that it doesn't change classes. So you have that. So it means that if you have a global group that moves non-local classes, it cannot have additive complete twists, right? And well, and then the thing is that if you have another current, if you have another current, then it's immediate that you can produce an additive twist. By smithing. So you have you can have your region is like this. R, I have the little smithing zone set, and then I can take some function that is 1 here and goes to 0 side and integrate J0 alpha x, right? And this is the charge corresponding to the region R. So this is alpha. This function is alpha. So with this, is immediately that the twist will be the exponential. And it is constructed locally with the current, so it's additive. But you can see that it's also complete. Why? Because you can have now if this is a charge for R. Let me call R bar all what is outside of the smithing zone, and you can have a charge for R bar that is the integral of 1 minus alpha. Yeah. Yeah, it's a unitary. Exactly. That's it. Yes, this is the thing. Right? But when you have this twist that is produced by a current, it's additive immediately, and then you can have the complementary current just by doing this, and this is additive in Z union the complement. So it must commute. So QR bar commutes with the maximal algebra of the region R, because it's an additive operator outside the region. But then QR plus QR bar is equal to Q, the global charge. So when you do commutations with your maximal algebra of the global charge, is exactly the same as the one of QR, because the other commutes. So it must be the case that the twist produced by the nether current is both additive and complete. So it must be the case that the symmetry doesn't change non-local classes. So sorry? is enough to have one, and then you have proved that in presence of the current, you can construct this. And this immediately tells you that you cannot have that the global symmetry moves the non-local classes, because it's additive and complete at the same time. Right, okay. Yeah, I've not. Oh, yeah? Right. Okay, I didn't know. Yeah, maybe. Well, in the discrete case, you can say something that is not as this one, but you can say that what happens is that these additive operators, or additive twists, or the complete twist, cannot coalesce, or how we call it, concatenate. We call it concatenate. They cannot concatenate to produce a bigger one. This is the problem, because they have a non-local operator on the boundary going around. In order to produce a twist that is gauge invariant, you have non-local operators on the boundary. So when you put the two together, they cannot form, the product of the two cannot form one that doesn't have a cut in the middle. Right. Well, this exactly cannot happen. This cannot happen. It's very, very similar to what I shown before about the tensor product. Well, here is the same, but instead of tensor product of Hilbert space or algebras, it's product of twist. The product of twist cannot concatenate, because otherwise immediately you have that nothing. It's just the twist doesn't act, the symmetry doesn't act on the non-local operators. If you have that, the symmetry doesn't act on the non-local operators. Yeah, I'm talking about Haussler variations. Yeah. Okay. And your on-site symmetry is side by side, let's say. Okay. 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 Well, here. Well, okay. Good. So then there is no there is no nether current wherever you have a global continuous symmetry that move classes, that mixes with the non-local operators generalized symmetry. And then you can see that all the counterexamples that have been provided of this, of the nether theorem, fall into this class. For example, you can say, well, let us try to, but one can ask, why is that this occurs very rarely? And the reason is that, the main reason is that when you have a non-local class, let's say A, that is not invariant the continuous symmetry, it means that the labels of non-local classes have to be continuous. And not only the A's, but also the B's have to be continuous. And this is quite rare, and in general what will happen is that it will produce something that is free and massless. Well, I will talk about this little if I have some minutes. So suppose the first, a simple case where you have the labels of the A and B is just a one parameter group. And then you have an abelian group, let's say. A1, A2 is just A1 plus A2 is an abelian group, and the same for B. B1, B2 is B1 plus B2. And then you have the commutation relations. So this is a situation in case you have your generalized symmetry is an abelian group, let's say, or one parameter is continuous. We need that it's continuous in order that the group moves the things. And you can say, well, the global symmetry group has to respect the fusion and has to respect the commutation relations. When you do that, you realize that you have only one possibility, is that the group acts of A carries it to A lambda, and B to B e to the minus A lambda, where lambda is the parameter of your group. And then it means that your classes A's and B's are non-compact, real line, and lambda is also the positive R, let's say, the reals. So in this case, you have non-compact classes, and the example of this, the typical example of this, is the Maxwell field in D equal to 5, because the Wilson loop will have dimensions, the charge have dimensions, and the symmetry group is the dilatations. So the dilatations just changes classes because the class is labeled by E, and E has dimensions. So it means that the Maxwell field in 5 dimensions cannot have a dilatation current. And this is kind of a typical example of where you have a dilatation symmetry and you don't have conformal symmetry. It's a quite trivial one. It's a free field. And then another example, now to get other examples, you need to get to two-dimensional A's. So A is a vector, B is a vector, and you have an abelian group. And then doing the same, respecting one parameter group, respecting the fusion rules and the commutation relation, you can see that it must satisfy. It must be the case that the vector A is transformed with the matrix linearly, and B is transformed with a transpose inverse matrix. So this is the transformation. Any one parameter group of matrices can be put there. And you can see, for example, one example of this is going to be a rotation in a two-dimensional plane, a rotation. And this is a U1 group, but this rotation implies that your A's and B's are going to be non-compact again. Non-compact again, and a typical example is, for example, you have two Maxwell fields, and you rotate between the two Maxwell fields, and this rotates between the Wilson loop of one and to the other. And another example is the duality symmetry in just one Maxwell field that rotates between electric and magnetic field, so it rotates between the top loop and the Wilson loop. So it changes classes. Both of them fall into this category. And another example is the graviton, a free graviton. A free graviton, H mu nu, that is a gauge field, but then you can produce the curvature that is antisymmetric here and here, and this curvature is gauge invariant, it's a linearized graviton in Minkowski space, and then with this you can produce antisymmetric fluxes, conserved ones, where these are constants, so these are conserved, and there are many more. In fact, there is a R20 of generalized symmetries, and then with these fluxes you can produce non-local classes that are non-invariant under translation, under Lorentz symmetries, because this thing will, these B's, these A's will violate rotation, etc. So the rotation and translations will change the classes. So it means that the graviton field doesn't have a stress tensor, it doesn't have a dilatation current, it doesn't have a rotation, duality current, for example, you also have duality. All these things, basically it doesn't have any current that you expect from a global symmetry, the stress tensor. And these two examples, this one and the two photons, is part of coincides with the idea of Weinberg-Witten theorem. Weinberg-Witten theorem tells you that if you have a massless particles of helicity greater than 1, greater or equal than 1, then you can a symmetry, a continuous symmetry under which these particles are charged, it cannot have a current, and for helicity greater than 3/2, it cannot have a stress tensor. And so this somehow explains the same thing from the point of view of generalized symmetries. And one can say, well, why? So if you try to construct examples, you immediately, most of the cases, you go directly to the cases where necessarily the generalized symmetries is non-compact. Non-compact meaning that is a group that is non-compact, but the complementary one also is non-compact. Both are, I mean, continuous and non-compact, because you can have U1 and the complementary one will be the integers. This is kind of non-compact, but it's discrete. So it's continuous non-compact. Well, in this case, you can see that in this case that we have a paper where we show that in this case, if you assume that the generalized symmetry is generated by fluxes of forms, as this case is, you necessarily, because of the commutation relations, the fields that are these forms are free fields or massless free fields. So it means that this explains somehow why most of the examples of violations of the Nair theorem are massless free cases. And it has to be massless and free. And then you can also play the game of looking for more complicated things in order to avoid this free case. Why is free? Because it's non-compact, the generalized symmetry. So I want some compact one. And you can take, for example, the case that the A's are U1 times the integers, and the B's that are dual to this are the integers times U1. That is the case of electromagnetic QED. QED has the Wilson loop. QED in 4 dimensions have the Wilson loops and the Toff loops in the same ring, only in 4 dimensions, and in the complementary region you have the same. This does not compute with this does not compute with this. Both of these are continuous because they have a U1, but the continuity happens in non-complementary parts of the thing. And then you can try to see if you have a continuous group that can play a game here, moving these things between themselves, and you find a unique possibility that is a so the discrete part, so let me, well, the discrete part has to be kept, so here, please change these things. So the discrete part has to be, cannot be moved. The discrete part cannot be moved. So the Toff loop, the charge of the Toff loop cannot be moved, but then the other part, you can take this, so it's kind of, the matrix is something like this, like 1, 1, 0, lambda. It's kind of a strange case where you keep invariant the integer charges and the other one move according to this rule. Well, this in principle would be a case where you can have an interacting theory that doesn't have a nether current. For you want a symmetry, a continuous symmetry without a nether current for interacting theory. Somebody can, this is the subject of Javier's talk in next week, and if somebody can guess which is this case. QED, yes. It's in QED for the chiral current, for the ABJ anomaly. Exactly time. Thank you. Okay.